All right, so to do another one of what we just did and do a complete cell description, we need the cell potential. So if we look down here at our two half reactions, you notice they're both reduction. So we always have to have a positive for a galvanic cell. So this one is the one that's going to be oxidation. So it's going to be Mn going to Mn2 plus 2 electrons. And so now we have a positive 1.18 volts. And so we add that to the negative 0.036 volts. 1.18 minus 0.036. We have 1.144. Significant digits. So our cell potential is 1.14 volts. Okay, so we got that. So we need to know the direction of electron flow. So it's going to go from the anode to the cathode, and anox, red cat, to help us remember. So the cathode is the manganese. Wow, that's oxidation. I just wrote that and then I still wrote it backwards. So let's try this again. Oxidation happens at the anode, so manganese is the anode. That makes iron the cathode. And the electrons are going to flow from anode to cathode. So electrons are flowing from the manganese to the iron. Okay? So if we drew this, we put our anode on the left, our cathode on the right with 1 molar solutions. With the nitrates. Oh, and to balance this equation, we would need to multiply this one by 3, multiply this one by 2. So our overall reaction is 3Mn plus 2 iron 3 ions gives us 3 manganese 2 ions and 2 iron. So we would have our solid manganese electrode going to our solid iron electrode. There's our direction of electrons. We would need our salt bridge. And there's our drawing. So that can get a little much. So we can do a line notation, which a line notation is really just a shorthand version of exactly what we would draw in the picture. So we have the anode electrode, which is the Mn, separated by one single line to the anode ion. Double line essentially represents the salt bridge to the cathode ion and the cathode electrode.